Hi everyone! In this video, we are going to explore the mechanism for this reaction using curved arrows. This reaction starts with a cyclic ketone called cyclohexanone. This compound is specifically a substituted aryl ketone where the carbonyl connects the benzene ring to a cyclic pentene ring. We are reacting it with methyl magnesium bromide, which is a Grignard reagent, followed by a neutralizing workup. A few notes on the reagent is that since it is a Grignard reagent, the carbon acts like it has a negative charge, which makes it extremely nucleophilic and reactive. And the magnesium acts like it has a 2+ charge. This reaction is an example of a nucleophilic addition to a carbonyl, resulting in the formation of an alcohol. We will begin by identifying the key players in the reaction. The nucleophile is the methyl group in the methyl magnesium bromide. Grignard reagents behave like a source of CH3-, meaning the carbon carries a partial negative charge and is, again, very nucleophilic. The electrophile is the carbonyl carbon in the ketone. This carbon is electrophilic because the carbon-oxygen double bond is polarized. With oxygen pulling the electron density away, this makes the carbon partially positive. We will now go over the curved arrow mechanism for this reaction. The first step to this is a nucleophilic attack. So that first curved arrow is going to start at the methyl group and point towards the carbonyl carbon. At the same time, the electrons in the carbon-oxygen double bond are going to move up into the oxygen. This will break the pi bond and form a new carbon-to-carbon bond between the methyl group and the carbonyl carbon and form an alkoxide intermediate where the oxygen now has a negative charge. So at this stage, we have a tetrahedral intermediate with a O negative. So I also had to go back in and add my lone pair electrons to the alkoxide intermediate, but the second step is going to show the alkoxide being protonated. This is the workup step. So the first curved arrow is going to go from the negatively charged oxygen to the proton, and this will be onto a hydrogen. On that same hydrogen that we're infiltrating, it's going to go into the oxygen of that same atom of the hydronium. This will form the final product, which is an OH group at that carbon. So now we have an alcohol in the final product. Here's the image of the final product, and this is the nucleophilic addition reaction. Since we had a ketone interacting with the Grignard reagent, the product is a tertiary alcohol. So we're now going to just review the electron flow in this section. For this reaction, the methyl group acts as a strong nucleophile because it has extra electron density. It attacks the carbonyl carbon, which is electron poor due to the electronegativity of the oxygen. This basically leads the pi bond toward breaking because those electrons are pushed into the oxygen, which can stabilize the negative charge better than the carbon. Finally, the oxygen is protonated because it is negatively charged and it is seeking stability by gaining the proton. This fourth section will review the regiochemistry and stereochemistry. In terms of regioselectivity, the nucleophile specifically attacks the carbonyl carbon rather than the alkene because the carbonyl is much more electrophilic. For the stereochemistry component, the carbonyl carbon is planar, meaning that the nucleophile can attack from either the top or the bottom face. So this ends up creating a new stereocenter. So the product can be formed as a mixture of stereoisomers unless one face is sterically favored due to the surrounding groups. Alrighty, so that pretty much wraps up the nucleophilic addition of a ketone reacting with a Grignard reagent, specifically methyl magnesium bromide. The methyl group acts as a really strong nucleophile that kind of attacks the carbonyl carbon to the ketone, which forms the alkoxide intermediate that is then protonated to give the tertiary alcohol.